Hi, and welcome back to our AP Chem Flipped Classroom, where we're continuing our conversation about rates and rate laws. So our last conversation, we talked about listing factors that affect reaction rates, understanding why those affect reaction rates. We used the method of initial rates to figure out differential rate laws, and we used rate laws to determine the effect of changing concentration of one of our reactants on the rate of that reaction. So today we're going to move from differential rate laws into integrated rate laws. And so we're going to be able to determine our order with respect to each reactant from concentration versus time data. You'll remember that with our differential rate laws, those relate concentration to rate. This relates concentration to time. And we're going to talk about applying half-life data. So let's go ahead and jump into our integrated rate laws here. And so when we are given concentration versus time data, that's our cue that we are going to be working with integrated rate laws. If we're given concentrations, differing concentrations and rates, then we're going to be working on differential rate laws. So when we look at integrated rate laws, when we look at a zero order rate, then that tells us that time versus concentration is linear. So that means that over each time interval, the change in concentration is going to be the same if it's the same time interval. First order reactions, time versus the natural log of concentration is going to be linear. So we're graphing to figure out what our order is going to be. And then our second order rate laws, or our second order reactions, time versus 1 over concentration is going to be linear. And so when we're given data, like we are here, where we're given time and we're given the concentration of either a reactant or a product, in this case, we can tell it's a reactant because it's disappearing, and we're asked to find the rate law. Even if we're not told that what we're finding is the integrated rate law, we know that we're finding the integrated rate law because we're given time and concentration information. We're not given a series of different reactions done at different concentrations the way we are for differential rate laws. Now, this is a lot easier if you have a graphing calculator with linear regression analysis. But even if you don't have that, we're going to talk about some ways that you can solve these problems. So first, let's look at solving it graphically. So if we take this same data and we just graph the concentration versus time. So here's our concentration data, here's our time data, and we graph that, and we find when we do the linear regression that our R-squared value is only 0.8891. So that tells us that this is not a very linear line. So that tells us this is probably not a zero order reaction. Now, if we were to graph time versus the natural log of concentration versus time, now we get a straight line. And you can see that in our regression results, our R-squared value is 0.99978. So that tells us we have a very good match here. And we remember that when we graph natural log of concentration versus time, if that gives us a straight line, that's a first order reaction. But let's go ahead and check our third option. So the third option is 1 over concentration versus time. And when we graph that, you can see clearly that this is not a line. And again, our linear regression agrees, and we have an R-squared value of just 0.8723. So our winner is time versus the natural log, or natural log versus the time. And that tells us that this is a first order reaction. And so we would write our differential rate law, this is the rate laws we've been practicing writing, as R equals K times the concentration of hydrogen peroxide. And the integrated rate law is the line that we just graphed. The natural log of concentration is equal to negative KT plus the natural log of the initial concentration. And so we can see that our y-intercept is the natural log of the initial concentration and negative kt here. So negative k is our slope. So how do we find that rate constant k? So before, when we had initial rates information, we just took the data from one of the lines once we figured out order, and we plugged it in and solved for k. Here, we can use the slope from our table. We can either calculate it as the change in the natural log over change in time, and we can find a slope that way. Or because we've done the linear regression analysis, we can find the equation of the line, which was negative 8.35 times 10 to the negative fourth times, and that was our slope. And since our slope was negative 8.35 times 10 to the negative fourth, that's also our k value. Remember, the k is the opposite of the slope, or the slope is the opposite of k. So we can find it either way. We can find it mathematically, or we can find it graphically. Okay. But if I don't have the calculator, or I don't have the time, or I don't know how to use my calculator, how can I find the integrated rate law? Remember, for zero order, the graph of concentration versus time is linear. That means that the change in concentration per unit time is always the same. It doesn't matter what the concentration is. First order, the graph of natural log versus time is linear, and half-life is constant. So half-life is how long it takes for half of the substance to react. So we'll come back to that. And then the second order, the graph of 1/, concentration versus time is linear. So how do we find this without graphing it? Well, if the change in concentration between time intervals is constant, then we know we have a zero order reaction. If it's not constant, we're going to move on, and we're going to see if half-life is constant. So we're going to pick a time when our concentration halves, and we're going to see if in that same time interval it halves again. If so, we know it's first order. And if it's neither of the above, then we know it's a second order reaction. So here's a practice problem. This one we're not having to determine from data. This one we're given a graph. And so we're told that this two monohydrogen dioxide molecules decompose into hydrogen peroxide and monatomic oxygen. And it occurs in the atmosphere. And in this experiment, they monitored the concentration of hydrogen dioxide over time, and the data was plotted. And you can see in our graph that what's graphed here is 1/, concentration versus time. So what's the rate law for this reaction? Well, that's very clearly a nice straight line. And since 1/, concentration versus time is linear, we know that this is second order with respect to the hydrogen dioxide. Okay, so we have another reaction here where we have dinitrogen pentoxide decomposing into nitrogen dioxide and oxygen. And our sample is placed in an evacuated container, and the pressure is measured. And so we're asked to find the order of this reaction. So what is the order of this reaction? So you can see from our data here that in 100 seconds, it goes from 150, pressure of 150 to a pressure of 75. And in the next 100 seconds, it goes from 75 to 38. So you can see that each time our pressure, and therefore our concentration, is halving. So because this has a constant half-life, we know that this is a first order reaction. So when we put all of it together, these equations here, the integrated rate laws, are on your equations and constants sheet. Okay, so for a zero order, we have concentration is equal to negative K, meaning the equation constant, times T plus the initial concentration. For first order, it's natural log, and for second order, it's 1 over concentration. Rate laws at the top here are our differential rate laws. So those are the ones we learned how to calculate already. And then we have, you'll notice that the K value is opposite of the slope for both 0 order and first order, but it is the same as the slope for a second order reaction. And you can see that this half-life here for a first order reaction is equal to 0.693 over K. And this is the only half-life equation that is given on your equations and constants sheet. So you would only ever be asked to calculate the half-life of a first order reaction. Okay, I hope that answers some questions and maybe brings up some more. And I look forward to seeing you in class.